name is Sergei Lapin, and my name is Anton Bogachev. We are PhD students from Immanuel Kant Baltic Federal University at Kaliningrad, Russia. And together we are working on Verilog modeling of region of interest fast level 1 pixel track trigger strategy for LHC. A series of feasibility studies was conducted in order to investigate performance and motivation for level 1 trigger based on pixel information, so-called level 1 pixel trigger, in the framework of high luminosity LHC.
In our modeling we are using Verilog, which is a hardware description language used to model electronic systems. It is most commonly used in the design and verification of digital circuits at the register transfer level of abstraction. It is also used in the verification of analog circuits and mixed signal circuits.
We start our work in University Paris Diderot, France. FAI4B was chosen for the basis of a new chip.
Our ongoing work focuses on the Verilog simulation of a region of interest similar to the one of FAI4B for Atlas experiment. This choice is based on the main features included in FAI4B, like sparsification, clusterization, level 1 trigger, distributed latency counter, and heat storage in the pixel array. The FAI4B architecture can be modified with additional latency counters to include a level 1 region of interest trigger that will cause the readout of a small fraction of the pixel readout chips. The first aim of this work has been to reproduce with a Verilog-based modeling the main features of this present FAI4B concept. This is what we present here. Model follows the structure of FAI4 architecture. It is thus divided into 4 subsections: the pixel, the region gathering 4 pixels and eventually neighboring pixels, the column gathering a number of regions, the board, which here designates the array of some number of columns. Okay, now let's review pixel heat processing in our model. When pixel is hit, the signal processing starts DUT counter. Once DUT counter surpasses some value, the signal processing searches for the first free among 5 DUT memory slot and starts corresponding latency counter in the region. It further includes a neighbor hit information if a neighbor pixel is hit within the same time sequence. The neighbor hit pixel information is identified by setting to 1 the corresponding bit in the detected DUT memory slot. Once hit stops, DUT data is being written to the previously allocated memory slot. Okay, now let's move to the region signal processing. Once the region receives found DUT memory slot signal from one of the pixels, it checks corresponding latency counter for the fact that it's not active yet and starting it. If corresponding latency counter is already active, then nothing happens. It means that the event that caused the checking happened in the approximately same time as the event that started counter, so they will be withdrawn or erased simultaneously. When trigger arrives, region checks for any latency counters that finished counting, and if there are any, then data from corresponding pixel DUT memory slots is being received and stored, and region is marked as ready to read out. If latency counter finished counting and there was no trigger, then corresponding DUT memory slots on pixels are being erased and latency counter resets. Once token arrives to the region, it checks is there any ready to read out mark or not. If yes, then region sends stored data to the column bus and passes token to the next level. If not, then token passes to the next region where process is taking place again. Column is responsible for data acquisition process based on the token passage logic and transferring end of column token to the next one once column token reaches end of column. When initiated, column instantiates amount of regions defined by amount of regions constant and connects them properly in terms of correct neighbor information transmission and defining correct path of token through instantiated amount of regions. Once column receives trigger signal, it checks that there is possibility to release token on first region, defined by column readout signal, which is based on end of column token passage, and then, if so, releases initial token and waits for end of column token, so column readout signal can be passed to the next column to repeat the process. Having fully achieved the current modeling of a readout architecture a la FEI4 with one level 1 trigger signal, we intend as a next step to work out the possible use of the second level 1 trigger signal that is included in this present architecture and see how it could be used for fast level 1 trigger based on region of interest level 1 trigger. Thank you for watching this video.